Hello, Tensor friends. Here is the solution to the problem of the day that was posted on 6/21, 26. Uh, Part A, derive the polar vector components as x being a function of r and theta, y being a function of r and theta, and then the opposite, r being a function of x and y, and theta being a function of x and y, from the following drawing. Now, I'm sure that no one had much trouble with this. So the cosine of this angle is the adjacent over the hypotenuse. The sine of this angle is the opposite over the hypotenuse. So that gives x equals r cosine theta and y equals r sine theta. Then we use the Pythagorean theorem, x squared plus y squared equals r squared. Square root of that is what we're looking for. Then if you just divide y by x, the r's cancel. You get sine theta over cosine theta, which is just tangent theta. Now you solve for theta and you get this. So we've got 1, 2, 3, 4 transform equations. That's what we wanted. Okay. Given the generalized equation for tensor transformations, okay, when you transform a tensor, you always use the format. It doesn't matter if it's a basis, it doesn't matter what it is, it's always the same, the format. For every index, you always have one Jacobian factor. And how you index it, you just follow the index. You just follow the free index. So I only have one in this case, so it always goes there. Then this becomes a summation index. This means the partial of xi prime with respect to x. So this is the partial derivative of the coordinate of the I prime frame versus the coordinate in the unprime frame. Okay? So we want to find ER and E theta. So the unprimed is R and the primed is XY. Okay? So that means the partial of x respect to REX, partial y respect to REY. We fill in what x and y are. We take the partial derivative with respect to r, which means that's a constant. Derivative of r is 1. That's a constant. Derivative of r is 1. And we get that. Okay, now we need to do E theta exactly the same way. We just changed the free index here. Theta, theta, theta. Everything else is the same. Okay, derivative of this with respect to theta is r is a constant. Derivative of that is minus sine. Here, r is a constant. Derivative of that is cosine. And here we have our two expressions, E theta, ER, and E theta. Using the Pythagorean theorem, this is part C, equation of ds squared equals dx squared plus dy squared. This is the arc length equation. Derive an expression for ds squared in polar coordinates. Okay, so how we get started is this. Now, x and y are compound arguments, right? They are a function of two variables. So you have to use the multivariable chain rule, which I'm sure you're familiar with. You can't just use a regular derivative. So dx is equal to the partial of x with respect to r dr plus the partial of x with respect to theta d theta. Okay? And you fill in what x here is here, respect to r, respect to theta. We just did this. And you get this dx. You square it, and you get these three terms. That squared plus 2 times this product plus this squared. Okay, now you do the exact same thing to y, and you get this. Okay, so the partial of this with respect to r, partial of this with respect to theta, you get this expression. You square it the same way. Now we got to add them together. So ds squared is equal to the summation of those two things. And you can see that luckily this cancels that. So you're left with this mess. Then you bring together dr squared and d theta squared. You factor out what you can. Here, I could factor out a dr squared. Here, I could factor out a r squared and d theta squared. That's the well-known identity 1. That's the well-known identity 1. And there it is. Okay? Part D, derive the metric tensor from ER and E theta in polar coordinates and compare its components to the metric found in part C. What I meant by that was compare it with this. All right, now we know how to do this. We've done it many, many times. The metric tensor is the dot product of the basis vectors. So here is ER and E theta. All right, so we start with ER dot ER, which is just ER squared. we get 1. We do er dot e theta, turns out to be 0. And you know the metric tensor is symmetric about the diagonal, which means that g theta r is equal to 0. Then we got to do g theta theta. We square that. We factor out of r squared. This becomes 1. We got r squared. All right, so here is our metric tensor in polar coordinates. Now look at this. The GRR component is the component for here. The g theta theta component, r squared, is the component for here. Well, what does that mean? Well, that means we can write this. ds squared equals the components of the metric tensor times the product of the infinitesimals, all right? And this is known as many names, the invariant infinitesimal arc length equation. Everyone just calls it the metric. All right, so this works in any coordinate system in any number of dimensions. It is an invariant equation. And it's made up of tensors, but the answer is a scalar. That's why it's invariant. Okay, wasn't that fun? I'll see you on the next one.